Okay. Good evening, everyone. My name is Devashish Panda. I'm a research scholar and Prime Minister Research Fellow at IIT Guwahati. So this semester, I have been allocated to this course, Structural Vibration, as Prime Minister Research Fellow, TSF duty. This course is instructed by Professor Arunasis Chakraborty, IIT Guwahati. So uh, for this introduction session, every Saturday we meet from 3 p.m. to 5 p.m. So today already we took the class, but during the class we faced internet problem, and I have found out that that recording has not done well. So I am recording it again for you. Although 6-7% were present during the class, so you have already been in the class, but for the video I need to record it again, so I am recording it. So basically today we will go through the free vibration case, where we will cover the undamped free vibration, damped free vibration, and then we will go to the concept of the logarithmic decrement, and we will see, using the concept of logarithmic decrement, how we can find out the damping ratio from the free vibration responses and all these things. Okay, so after every session you will get the link of the video recording session, also solved assignments, and when we will solve the assignments using MATLAB, so you will get us MATLAB scripts also. So for this recording session I need to record it again while I have taken the class 2 hours and you were present, but the recording was not done properly, and we have faced different kind of many times we have lost the connections. So just for today, I am recording it again. So during the last session, we have understood the concept of the dynamic system, whom we call a dynamic system. We have also understood the concept, the difference between the static analysis and dynamic analysis. We have went through the component of a dynamic or vibration system, like mass, stiffness, and damping, how to model them. We have also covered the concept of the degree of freedom, and we have formulated equation of motions using D'Alembert principle as well as Newton's second law, and using the energy principles. So all these things also we have covered the concepts of simple harmonic motion and all these things. So today we will go through the free vibration of a single degree of freedom system. Single degree of freedom system means that mass can move only positive x or negative x direction. That means to define the position of the displaced mass, we just need one independent coordinate, and this is that displacement x. Okay. So as we have formulated the equation of motion for a single degree of freedom system on the last class, so broadly the vibration system can be categorized into two parts. First, the free vibration case, and second is the force vibration case. So vibration system, if I categorize it broadly, vibration systems, so we can categorize it into free vibration case. Free vibration, that means the system or the body is free from the external harmonic loading or external loading, so free, and it's vibrate on by its initial conditions, free from the external forces, but it will vibrate due to the initial conditions whatever we have provided. So first case is the free vibration case, and another is the forced vibration case, where the vibration is generally occurring due to the influence of the external loading, forced. Now in free vibration, already we have covered the concept of damping. So if damping is not present, that means C, the damping coefficient is 0, we call it undamped free vibration, and again if the damping terms is there, C not equals to 0, we call damped free vibration. That means, say for example, here there is a SDOF system, and say for example one external loading Ft is also there. Now if I want to write the equation of motion for this system, what will be the equation of motion for the system? Mx double dot T plus Cx dot T, because we are considering the viscous damping or viscously damped system, and Kxt is equals to the external force F of T. We can now, if F of T is equals to 0, that means there is no external loading is present. The system is vibrating by its initial conditions and at its natural frequency, we call free vibration. Okay. Now, in free vibration case, two cases can be there. One with damping, another without damping. So today we will cover the free vibration part, where we will solve the equation of motion of a undamped free vibration case where damping is not present, and again we will solve the equation of motion for the damped system where damping is present. Now for the force vibration case also we will have two categories. One is where damping is not present, we will call undamped force vibration, and again if damping is present there, we call it damped force vibration. Okay, we will cover it on the next interaction sessions. Great. So free vibration, what I said, free vibration means the structure is vibrating with its initial conditions, free from the effect of the or influence of the external forces. Right? That means no external forces is applied. So how the vibration is occurring? The vibration is occurring due to the initial condition. Say for example, say we have a spring mass system, and I am modeled the system like this. Say one concentrated mass is there, and the column represent the stiffness. Now I provide some initial displacement, say for example initial displacement of x naught, and leave the thing vibrate. That means I am providing the initial displacement. Say for one case one, you can see one initial displacement is provided, slope is 0, that means no initial velocity is provided, only the initial displacement is provided, and the system will vibrate. Now if damping is not present there, it will vibrate freely, over infinite time of period. Now if we provide the initial velocity, here you can say we can provide the initial velocity also. Here the slope is there but the initial displacement is 0, and leave the system vibrate. So using initial, giving some initial velocity, the motion can generate within a body. Now here for the case 3, we can see we provide some initial displacement x naught, and also some slope is there, that means initial velocity is also there, and we leave the system vibrate freely under this initial condition. So we call this phenomena, or we call this vibration, as free vibration. That means the structure is vibrating without any influence of the external force, but the motion is created or generated due to the initial conditions. Okay. Now these things are there. So free vibration, we have understood what we call the free vibration. That means the structure is free from the external forces, but due to some initial conditions we are providing to it, the motion will generate and motion will continue. So free vibration, there can be damping present on the free vibration, or damping not present on the free vibration case. So first case we will see where the damping is 0. That means the system is free from the damping phenomenon. Damping, we already discussed about the damping little bit, the viscous damping thing. Damping is nothing but the phenomena by which the amplitude of vibration get diminishes over time, or the energy distribution mechanism within a vibration system. So first case we will see for the undamped free vibration case, where damping is not present there. That means C is equals to 0. So we consider a single degree of freedom system where stiffness is represented by K, mass is represented by M, and this is the degree of freedom. That means X is the coordinate. So if we draw the free body diagram of this system, obviously what we will see, the restoring force due to the spring action, and here we have modeled the stiffness as linear stiffness. So the restoring force due to spring action Fs will generate, and that is nothing but K into X of T. Also, the damping is not there, so damping force will not generate. So we will have the inertia force Mx double dot T. Now, if we write down the equation of motion, we will have like this: Mx double dot plus Kx dot is equals to 0. Now, look at the equation. It's a second order homogeneous differential equation with constant coefficients. So now, if we look for the solution of this equation, the solution, what we will get? The trial solution we will can get like this: x is equals to some constant c e to the power st in the harmonic terms. So now differentiate it with respect to t twice. So we will get x dot and x double dot. So we have now x, x dot and x double dot. Now put all these values in the equation 1. What we will get? We will get c, the constant term, outside the bracket, then m square plus k e to the power st is equals to 0. Now e to the power st cannot be 0 because it's one of the harmonics, one of the solution of this equation, so it cannot be 0. So what we left with? We left with this part, m s square plus k is equals to 0. Now if we solve it, we will get two roots. One is plus I under root of k by m, and another is minus under root of k by m. Now, if we simplify it, we know the natural frequency omega n is nothing but root over of k by m. And what is the natural frequency? What is the definition of the natural frequency? Natural frequency is the frequency at which one structure or system vibrate freely or vibrate with the initial conditions, more precisely. So our root of this equation, two roots of this equation becomes plus minus I omega n. So first root plus I omega n, second root minus I omega n. Now these are the root of the equation. Now we can write this equation, or the general solution of this equation we can write in the terms of the linear superposition of these two harmonics, like x of t is equals to nothing but a1 e to the power s1t first root with respect to plus a2 e to the power s2t with respect to the second root. Now we will use the Euler equation, and Euler equation says e to the power I omega nt is nothing but cos omega nt plus I sin omega nt, and e to the power minus I omega nt is nothing but cos omega nt minus I sin omega nt. Now if we put all these things in this equation and simplify it, we will get the general solution like this: xt is nothing but a cos omega nt plus b sin omega nt, where a and b are the constant. We can easily find them out from the initial conditions. Initial conditions, because it's a free vibration and we are providing the initial conditions. Either we can provide the initial displacement, we have already seen. Either we can provide the initial displacement, or we can provide initial velocity, or we can provide both. So from the initial conditions, we can find out the value of a and b. Now let's see how we can find out the value of a and b. So xt is nothing but a cos omega nt plus b sin omega nt. Now at t equals to 0, that means at initial position, we are providing the displacement xt is equals to x naught 0. Say for example x naught 0 have some value, say 5, 10, 15, whatever. For now it's defined by x naught 0, and at the initial condition t is equals to 0, we are providing some initial velocity which is x naught 0. Now at t is equals to 0, put all these values in this equation 4. So what will happen? At t is equals to 0, That means xt is equals to 0 equals to a. Now cos 0 will become 1. So at t equals to 0, the initial displacement will be x naught. Already we have provided. So a plus, so this part will get cancelled out because sine 0 will 0. So we have a is equals to the initial displacement x naught. Now again differentiate this equation with respect to x. We will get x dot is equals to nothing but minus a omega n sine omega n t plus b omega n cos omega n t. Now at t is equals to 0, impose the second initial condition. At t is equals to 0, we know that x dot of t, that means the velocity, is x naught of 0. Now put all these things, you will get that b is equals to x naught dot or x dot naught, that means the initial velocity at times equals to 0, x dot naught divided by omega n. So we have found out the value of the constants a and b. Now put this in the equation here, equation 4. So we'll get the final solution in the terms of this. Xt is nothing but x naught cos omega n t plus b value x dot naught, that means the initial velocity, divided by the natural frequency sine omega t. So this is the final solution for the displacement of a undamped free vibration case. Okay, now once we have the equation for the displacement, we can solve for velocity. Just you need to differentiate it. So x dot t is nothing but minus the initial condition, initial displacement x naught omega n sine omega n t plus x dot naught cos omega n t. And again, if you differentiate it, you will get the expression for the acceleration also. So now, what we have understood for the free vibration case? For the free vibration case, the structure is vibrating without any influence of the external loading. So how the motion will generate due to the initial condition? Either we can impose the initial velocity, initial displacement, or both. So for this system, if we know the initial displacement, initial velocity, if we know the properties, and from where we can calculate the natural frequency of the system, we can easily find out what will be the response at t is equals to different time instance. So for example, t equals to 2, t equals to 3, we can easily calculate. Simultaneously, we can calculate the velocity and acceleration response of a undamped free vibration case if the initial conditions and the natural frequencies are provided, or the system properties are provided, so that we can calculate the natural frequency and we can find out the responses at different time instances. Now how we can find out the amplitude? Already amplitude, it's very easy. Like, we have the solution for the displacement x of t, that means at any time instant t, the displacement will be x naught, the initial initial displacement cos omega n t, initial velocity divided by omega n sine omega n t. Now if I consider x naught is equals to c cos phi and simplify the equation, we have found out that c will be nothing but under root of your a square plus b square. That means that a and b we have already found out. X naught initial displacement square plus initial velocity divided by omega n that square. So this c is nothing but the amplitude of the motion. So here we have seen that for this case we have provided some initial displacement and also initial velocity. Say x dot naught we have provided, and we have provided some x naught, and leave the system vibrate. So if damping is not present there, it will vibrate with that amplitude c is equals to this. Right, now how we can calculate the phase phi or theta? we can easily calculate. It's nothing but tan inverse P by A. So tan inverse initial velocity divided by initial displacement and omega n, right? So by this way, for a undamped free vibration case, if the initial conditions and the system parameters are provided, we can calculate the displacement response, acceleration response, velocity response at different time instant. We can also calculate the phase, we can calculate the amplitude and different kind of responses. Now, what I already said, that omega n is called the natural frequency, or more precisely, we can call it the natural natural circular frequency. Wn is called the natural circular frequency. That means the frequency in which a structure vibrates due to the initial conditions, free from the external loading. So more precisely, the definition says it's the natural circular frequency, root over k by m. The unit is rad per second, and where f is called the natural cyclic frequency. That means the number of cycles required, or the number of cycles per second, or we can say, and the unit is hertz. So what will be the natural time period? Natural time period Tn is defined as nothing but twice pi by omega n. So if damping is not present there, say for example here, for this motion we are providing some initial displacement, initial velocity, and leave the system vibrate freely. So if damping is not present there, so this system will keep vibrating uh, for a infinite time period. Okay, and natural frequency means it's vibrating freely. That means without any external forces. So omega n here is called the natural circular frequency. That means how much radians each cycles it covers, or how much radian covers in each cycles. So it depends on mass. Two properties. First property is nothing but mass, and the second property is stiffness, right? Time period twice pi by omega n. That means the time required, natural time period, if I want to define it, so time required for the undamped system to complete one cycle in free vibration, we call natural time period. Okay, so for a undamped free vibration case, we have found out the expression for the displacement, velocity, and accelerations. So here three cases we can see here. First case, we are providing some initial displacement x naught, some initial velocity, and leave it to vibrate. It will vibrate. Damping is not present there, so amplitude will not get diminishes. And this is the time period, or natural time period Tn for the system. So here for the second case, we have seen that only initial velocity is provided, not initial displacement is given. So only initial velocity, or under the action of the initial velocity, the system will keep vibrating. Now the third case, we have seen only initial displacement is provided, slope is 0. That means no initial velocities are provided. So now you understood, or all of us can correlate, that what we call the free vibration. That means a structure is vibrating freely without any external force. The motion is created due to the initial condition. Here we can see three initial conditions, either initial displacement, initial velocity, or both we can supply as an input to get the vibration of the vibration of the system. Now few concepts, like if we have, quickly we will go through that few concepts. So if we have two systems, okay, so for the two systems, mass is same. Say two systems, we have 1 and 2. Two dynamic systems are there. So mass for these two systems are same, but stiffness of the first system is more than the stiffness of the second system. So obviously we know that natural frequency is nothing but under root of k by m. So obviously the omega 1, as k is greater, so omega 1 will be greater than omega 2. That means the stiffer structure or the structure with higher stiffness will have higher natural frequency and smaller time period, right? Here we can see. Now if we want to keep the stiffness k1 is equals to k2 same, but for the second case, say for example m1 is greater than m2, so obviously look at the expression for natural frequency. Obviously the second natural frequency of the second system will more than the natural frequency of the first system. That means that heavier structure or the structure with higher mass has lower natural frequency and higher time period, right? Vice versa, lighter structure have higher natural frequency and lower time period and all these things. So this kind of conceptual question like two systems may be given or can be given and asks like which system has higher natural period, which system has higher natural frequency. If mass is constant, stiffness is varying. If stiffness is constant, mass is varying, and all these things. So I hope you get this concept. If this kind of conceptual question will come, how to cater with this. Now, now let me check the recording is going on. So, what I said, like in a free vibration, if the damping is not present there, that means the vibration or the amplitude of the vibration will not get diminishes over time. So how in a free vibration case, how the energy is actually get balanced. So we will talk it about it, then we will move to our next session. Okay, so let's say for a vibration system we provide some initial displacement x naught, and we also provide some initial velocity dot. Now for this system, how the total input energy is actually balanced. So we will see the phenomenon. So total input energy, what do you know? The total input energy is nothing but the strain energy plus the kinetic energy. Why I am using the strain energy? Because this energy is due to the spring action. So strain energy, you can write it down half into k into x naught square, whatever the initial displacement I am providing to the system. What will be the kinetic energy? Kinetic energy will depend on the initial velocity. So half m into x dot naught square, right? So this is the total sum of these two is the total energy I am providing to the system. Now see how this thing get balanced. So say for example here I am considering a point A. So for point A, here the amplitude of the vibration is maximum, right? So for point A, the strain energy will be maximum, right? Now here look at this point, here the slope is 0. That means the velocity of this point is 0. That means my potential energy, sorry, kinetic energy half into m into the initial velocity square. So velocity is 0, that means 0. So at this point, a point, if we see the energy or if you look into the energy, so at a point the strain energy will be maximum because the amplitude of the vibration is maximum, but the slope, that means the velocity, gets 0. So kinetic energy is 0. Now consider point B here. So in B, what do we see? The displacement, that means x naught gets 0 because this is the 0 ordinate. But here we have the maximum slope. That means we will have maximum velocity. So at point B, the strain energy is 0, but kinetic energy get maximum. So by this way, at each point, the kinetic energy converted to potential kinetic energy and strain energy exchanges, and the energy get balanced. Energy get balanced due to the initial conditions. So by this way, in a free vibration case, the energy, total energy of this vibration is actually uh, conserved, right? Now, so till now, we have understand uh, the free vibration case, whom we call free vibration. We have found out the solution for the displacement, velocity, acceleration under the initial conditions. We have the concepts of the circular natural frequency, cyclic natural frequency, natural time period, all these things. So now we will quickly solve some problems so that these concepts will get more clear. So the first problem, what the first problem says, evaluate the natural frequency, for the portal frame shown in figure 1.1 if the initial displacement, okay, the initial displacement is 15 mm and initial velocity is 20 mm. So without any initial conditions, we will not get any kind of vibration. So obviously initial conditions will be there. So x naught is 15, x dot naught is 20. What is the amplitude and displacement at t equals to 1 second? Given the flexural rigidity of this column AB and CD is 30 into 10 to the power 12 Newton mm square. So what do we need to do? First, we need to find out the natural frequency. And what is the formula for natural frequency? Omega n is nothing but under root of k equivalent by m. So first we need to find out the k equivalent. So here for the portal frame, we have two columns. So for the column, for a single column, what do you know? The k is nothing but 12 EI by L cube. So for this column also, we will have 12 EI by L cube. Now we have two columns, so we need to sum them up. So here EI value, EI for AB and EI for CD is given. Only the sorry, only the length is varying. So we have all the inputs. Just simplify the equation. K equivalent is equals to 12 EI AB of L cube AB plus 12 EI CD of L cube CD. Now put all these things, you will get the K equivalent is 75061.73. Please check the calculations once. Okay. So Newton per mm. Now once we have found out the K, we have the weight. From weight we can find out the mass and we can calculate the natural frequency. So what will be the natural frequency? Wn will be nothing but K equivalent by m. So K equivalent already we have calculated as 75061.73 divided by m. So here the weight is provided in 20 meganewton. So Newton, I have converted it 20 into 10 to the power 6 divided by G, 9.81 meter per second squared. So it's for the simplification of the units, I have converted it 9810, and the omega n is comes as 6.07 rad per second, or we can say the f, the cyclic frequency will come as 0.165 hertz. Once we have the natural frequency, we can easily calculate the time period or natural time period. So Tn will be nothing but twice pi by omega n. Now if you put all this in this equation, you will get the time period as 0.1.04 second. So now we have mass, equivalent stiffness, we have the time period, we have the natural frequency, all these things. Now second part of this question asks, what is the amplitude and displacement at t equals to 1 second? So what was the equation for the displacement for undamped free vibration case? Just we have solved that xt is equals to x naught cos omega nt x dot naught by omega n sin omega nt. Now you have the values of x naught initial displacement as 15 mm. We have the value of x dot naught, the value is 20 mm per second. We have t is equals to 1 second. So put all these values, you will get the equation of for the displacement as a cos 6.07 t minus 5. Now we need to calculate the a first. A is nothing but the amplitude of the motion. A is nothing but, we have seen, under root of initial displacement square plus initial velocity divided by the natural frequency, that square. Now put all these things, you will have the A is equals to 15.35 mm. So this is the amplitude. What will be the phase? Phi. Phi is nothing but tan inverse of B by A. So tan inverse of x dot naught divided by x dot omega n. Okay. So we have now all the information. Now, so t is equals to 1 second. What will be the displacement? Now here in this equation, just put t is equals to 1 and a is equals to 15.35. Phi is equals to 12.41. So you can find out the displacement response at t equals to 1 second. Now if you need to find out the what will be the velocity at t equals to 1 second, you just need to differentiate this equation and put all these values at t equals to 1 second. You will find out the velocity at t equals to 1 second. Now let's move to the second question. Similar kind of question. What this question says, a concentrated load of 20 kilonewton is applied at the free end of a cantilever beam of 200 into 200 mm. Okay, so let's draw the beam simultaneously. So we have a cantilever beam and 120 kilonewton load is applied at the free end of this cantilever beam. Great. The cross section is given. It's a square beam, 200 mm into 200 mm. Okay. E is also provided. Initial conditions are provided. X naught 0 is equals to 2 centimeter. That's means initial displacement we are providing 2 centimeter and initial velocity we are providing 1.5 meter per second. Neglect the weight of the beam. Great. So first, what we need to find out? Say we will find out the omega n. We will find out the f. We will find out the t. How we can find out the omega n or the cyclic frequency fn? So first we need to find out the stiffness of this or the equivalent stiffness of this system. So it's a cantilever beam. One concentrated load is acting on the free end. So what will be the deflection at the free end? Del is nothing but PL cube by 3 EI. Right? Now we can find out the K. K is nothing but, we know, P by del. We have the P value, we have the del value. So we can calculate the stiffness. So stiffness will be P by del. Now put all these values. You know the value of P. You know the value of delta. Delta is nothing but PL cube by 3 EI. Simplify this equation. Put all these things. You will get the stiffness as 5107200 Newton per meter. Great. The stiffness part is done. Now, mass, effective mass. Here, the beam is considered as massless, but a concentrated load as a dead load is continuously acting on that. It's a dead load, not that harmonic load. So we need to find out the effective mass due to that load. So what will be the effective mass due to the load? It's nothing but P by G. So P is 20 kilonewton, means 20,000 Newton divided by 9.81. So we will have 2038.74 kg as mass. Now we can easily calculate the natural circular frequency omega n. So natural circular frequency will be nothing but under root of k by m. So what was the value of k? K is nothing but 5107200 and m effective mass is this, so comes as 50.05 rad per second. Now once we have the omega n, we can find out the natural time period Tn, nothing but twice pi by omega n, and it comes as 0.125 second. So what will be the natural cyclic frequency? Fn is nothing but, either you can write it down 1 by t. So 1 by t will be 8 hertz. Now for this system, we have all the parameters like what is the stiffness, what is the natural frequency, what is the time period, and all these things. Now for this system also, if asked that find out the displacement at t equals to 1. So what you need to do? Again, you need to use that displacement equation. So xt is equals to x naught cos omega nt plus x dot naught by omega n sin omega nt, right? So you have all these values put in these equations, you will find out the displacement response at t equals to, say, for any seconds, you can find it out. Say 1, 2, 3, 4 seconds, you can find it out, right? So move to the next question. Oh, yeah. Also, t equals to 2 seconds, you need to calculate the displacement. Okay, great. Then, so t equals to 2 seconds, we have omega n already we have calculated. We have all these things. So what we need to do? We need to use the equation or expression for displacement, and for undamped free vibration case, the equation for displacement is nothing but xt is equals to x naught cos omega nt plus x dot naught, already we have just derived it, dot by omega n sin omega nt. So x dot is the initial displacement, so 2 centimeter is provided. X dot naught is the initial velocity, here 1.5 meter per second is provided. Now you just need to put it all these things in these equations. So x t is equals to 2, we can easily find it out, the value of the displacement, and it comes as 5.65 mm, right? If in this question, if asked that find out the velocity at t equals to 2, so you just need to use this equation x dot t, or first you need to differentiate the displacement equation once. You will get the equation minus x naught omega n sin omega nt plus x dot naught cos omega nt. So put all these values, you will get the expression, or you will get the value of the velocity at t equals to omega n. Already you have calculated on the previous slide, 50 point something 05 rad per second. Now if in that question, same question, if asked, okay, find out the accelerations at t equals to 2 seconds, so you just need to use these equations, you will get the accelerations at t equals to 2 seconds. So till now what we have covered, just we will quickly go through it and then we will move to next portion. So first we have covered the free vibration case. Free vibration, that means the structure is undergoing free vibration when it is disturbed from the initial equilibrium conditions by providing initial velocity, initial displacement, or both, and leave it to vibrate. That means it is completely free from the effect of or the influence of the external forces. It's vibrate due to its initial conditions only. Then we formulate the equation of motion and solve this equation of motion for the displacement, velocity, and acceleration cases. And also we have seen that how to calculate the amplitude and phase of a undamped free vibration case. So if the phenomena is undamped, that means damping is not present there. So the vibration will continue for the infinite time period. But in practical cases, it is not possible. Somehow the damping will present and the amplitude of the vibration will get diminishes over the period of time. So for the damped cases, we will see that how this amplitude of vibration will get diminishes and how to counter with that. Okay. So now we we will go through the damped free vibration. That means damping is present there. So already we have discussed the damping phenomena. Like damping, actually we can define it like that. The damping is a property which makes the vibration diminishes its amplitude, or we can say it's nothing but the energy dissipation mechanism in a vibration system. So here we can see for this system we have provided some initial velocity and leave it to vibrate. But if it is a undamped case, what will happen? Like the amplitude will be same in each cycle. But here we can see the amplitude of the vibration will get reduced or diminishes over the time. And this phenomena occur due to the damping. Okay, so damping, what is damping? What we can define the damping? Damping is nothing but it's a property which makes the vibration diminishes its amplitude, right? Like for example, if we have a pendulum, say here the pendulum, here the portion. Now we provide some initial displacement and leave it to vibrate. So what will it do? It will vibrate, and obviously there will be drag force of the wind, there will be friction here. So that means damping will come, and over the period of time what will happen? The amplitude of the vibration will get diminishes like this based on the quantity of damping present on this system. So damping we have understood, it's nothing but the energy dissipation mechanism in a vibratory system. So damping sources, from where the damping can come. So damping may come from repeated straining, friction at joint, temperature due to straining. Different kind of damping devices are there. Like we have discussed the viscous damping model. There are friction damping model. There are other passive and active kind of damping models. So there are different kind of damping models are available in the market. The main purpose is to reduce the energy of the vibration. So for now, we will stick to the viscous damping model. In viscous damping, what I said already, we have discussed that in viscous damping model, the damping force is considered proportional to the velocity of the motion. That means Fd, we can write it down like that, C into x dot of t. So this is the simplified model for the viscous damping. C is nothing but the damping coefficient. Okay, that means it's nothing but the measurement of the energy dissipated in a cycle of a free vibration. So we will see how we can quantify or measure the damping ratios from the free vibration response case using the concept of the logarithmic decrement. So now we will focus on viscously damped free. So here obviously the viscous damping is present. So viscous damping model, already we have discussed the model of the viscous damping. Now we will formulate the equation of motion and solve it. So viscously damped free vibration. Free vibration. That means the external loading PT is 0. So it's a very simple kind of derivations. So I will go through it one by one, line by line. So here we have a spring mass damper system. If we draw the free body diagram, what will happen? We will have the spring force K into X linear spring. We have viscously damping model. Damping force Fd is equals to nothing but C into X dot. We have the inertia force Fi. So inertia force will be nothing but mx double dot of t. Now, if we write the equation of motion for this system, what will look like? Mx double dot of t plus cx dot t plus kx of t equals to 0. So this is the equation of motion for the damped free vibration case. Damping is present there and we are modeling it considering the viscous damping model, right? So this is equation number 1. So look, it's also a second order equation. So the solution again I have considered it xt is equals to d some constant e to the power harmonics e to the power st. Now differentiate it once and twice and put the values in equation 1. What will happen? We'll get like this: ms square plus cx plus k bracket d e to the power st is equals to 0. Now d e to the power st cannot be 0 because it's one of the solution, it's a harmonic, so cannot be 0. So obviously we will left with this part will be 0. So if we simplify it, we will find the root as minus c plus minus root over c square minus 4 mk by twice m from the Siddharacharya root. Now if I simplify this little bit, what I will get? I will get like this: minus c by twice m plus minus under root of c by twice m square minus k by m square. Now this is my equation of motion. I have two roots. So what will be the general solution? I can write it down xt in the terms of you know linear superposition of the harmonics. So d1 e to the power s1t first root plus d2 e to the power s2t. Great. Now just instead of s1 and s2, you can write down these two roots. Now the final equation of most or the general solution will look like this. It is looking like this, but I will explain step by step. It will very easy. So before going further steps, till now what we have done, we just formulate the equation of motion. We consider a general solution for the second order differential equation. We find out the root and just simplified the general solution of this equation. Now before going further, we need to understand some definitions and some concepts. So first thing is the critically damp, critically damping, C shear. What do you mean by say critically damping case? So critically damping is the damping required to remove the complete vibration energy from the system. Okay. So critical damping means the damping required to completely, remove the vibration energy from the system, completely remove the vibration energy from the system, right? C shear, and it's actually the function of mass and stiffness. So we can write it down like this: twice m omega n. Now again we define a ratio zeta or eta, both represent the damping ratio. It's nothing but C by C shear. That means it's the ratio, the damping present on the system, and the damping required to completely remove the vibration energy from the system. It's called the damping ratio. Okay. So further we can simplify this equation like theta is equals to C by twice m omega n, because CCR is equals to twice m omega n. And also we know that omega n is equals to nothing but under root of k by m. Okay. So From here, we can write it down like this: C by M is equals to twice zeta omega n. So we need this definitions and conditions to solve this, you know, damped vibration case, damped free vibration case. So depending on the damping ratio, there can be three cases. First, critically damping case, zeta is equals to 1. For underdamped system, zeta less than 1. For the overdamped system, zeta greater than 1. So we will solve for these three cases and we will see under which cases the oscillation will occur and under which cases, it will be aperiodic and no oscillation will occur. Okay. So now go back to the general solution of this damped free vibration. So we were here. Now simplify this equation, C by twice M. Now we have the simplified version of the C by twice M, because C by twice M is equals to xi omega n. So simplify it. Roots will become minus zeta plus minus under root of zeta square minus 1, and the simplified version of the general solution will become x of t is equals to d1 e to the power minus first root s1t d2 e to the power second root s2t. So the final solution will look like this. Now if, say for example, we already solved the undamped free vibration case, so zeta is equals to 0, so our equation will look like the general solution of the undamped free vibration case general solution. So here, this is the equation of motion for the damped free vibration case. Now what I said, we have three cases. One for the critically damped system, when zeta is equals to 1. We have zeta less than 1, we call under damped system. Most of the engineering applications, most of the engineering structures actually under damped system. That means the damping present on the system is less than the damping required to completely remove the energy from the vibration. Like critically damped, why we need to think about the critically damped system? Like shock absorber of a car or bike. Whenever the vibration will come, the absorber will, as soon as possible, the absorber will absorb this vibration energy. That means we need to design like that. Okay, critical case, as soon as possible the energy of the vibration will get diminishes or get absorbed by this phenomenon. So let's say for the first case we will solve. So for the first case, we are considering the undamped case, because underdamped case, because only the underdamped case we will see, only the underdamped cases we will get the oscillation. For this rest two cases we will not get any kind of oscillations. So undamped case, that means zeta is equals to less than equals to 1. That means the damping present on the system is less than the critical damping. And what is the definition of critical damping? Few times back I have said that critical damping, the damping required to completely, remove the vibration energy from the system. So now when zeta is less than 1, we will have two roots as a form of complex conjugate. Just put it in these equations, you will find out. Right? 1 2 will be, 1 will be minus zeta plus I under root of 1 minus zeta square omega n, and second one will be minus zeta minus I under root of I under root of I under root of I 1 minus zeta square. Now in the general solution, you just put the root. Here we have written out the general solution for it. d1 e to the power root s1t, d2 e to the power s2t. So just write it down in this form. So d1 e to the power the first root, d2 e to the power the second root, right? So we have the simplified version. So e to the power xi omega n t, I just take it out from the bracket and we left out with d1 e to the power I under root of 1 minus xi square, d2 e to the power I under root of 1 minus xi square. Now we will use the Euler's equations. E to the power I theta is nothing but cos theta plus I sin theta, and e to the power minus I sin theta is nothing but cos theta minus I sin theta. Now use these equations. So we will get our final general solution as xt is equals to e to the power minus zeta omega n t, the exponentially decaying function, multiplied by a cos under root of 1 minus j square omega nt plus b sin 1 minus j square omega nt. Okay. Now, here we define, here the damping is present. So, we define the natural frequency as damped natural frequency omega d. So, for this system where damping is present, we define the natural frequency as the damped natural frequency, and the relation between the damped natural frequency and natural frequency is nothing but omega d is equals to omega n under root of 1 minus zeta square, and zeta is nothing but the damping ratio, zeta and eta. So now here instead of this term, if we write it down omega d, our equation looks like this. Xt is equals to nothing but e to the power minus zeta omega nt under bracket a cos omega dt plus b sin omega dt, and d is called the damped natural frequency of the system, and a and b can easily be found out from the initial conditions, because we are talking about the free vibration case, and for the free vibration case obviously the initial condition will be there, otherwise the motion will not generate. Great. So initial condition, let's find it out from the initial conditions a and b and complete the solutions. So our general solution become xt is equals to e to the power minus zeta omega nt. This is nothing but the exponentially decaying function a cos omega dt plus b sin omega dt, and omega d is nothing but damped natural frequency. So now consider the initial condition. X t is equals to 0, the initial displacement is x naught. At t equals to 0, the initial velocity is x dot naught. Now here in this equation 1c, just put t equals to 0, x naught is the initial velocity. So we left out with a is equals to x naught. Because the sign part will get 0, we will have a into 1, and omega and t equals to 0, that means this part will 1. So we will have a equals to x naught. Now differentiate this equation with respect to t. So we will have x dot is equals to minus zeta omega n e to the power minus zeta omega nt a cos omega dt plus b sin omega dt plus e to the power xi omega nt minus a omega d sin omega dt plus b omega d cos omega dt. Now for this case we have the initial condition, the velocity at t equals to 0, the initial velocity is x dot naught. Right, from here after simplifying we will get b is equals to x dot plus x dot naught plus zeta omega n x dot divided by omega d. So now we have the a and b, the constant term. So now put the value of a and b in this equation. We will get the complete solution of the displacement for viscously damped free vibration cases. So it looks like xt is nothing but e to the power xi omega nt cos x naught, the displacement initial displacement plus omega plus initial velocity x dot naught plus xi omega n x naught divided by omega d sin omega dt. Right, now look at this, damping is present. Now what I said, damping actually what it does, actually reduce the amplitude of the vibration. So here we can see, here we have provided some initial velocity and leave the system vibrate. Now we have seen that envelope actually dictates by this term e to the power minus zeta omega n t. How much your zeta, that will dictate the slope of this curve and all these things. So for the free vibration case we have seen that my equation of motion was xt. For the general solution for the displacement case was xt was a cos omega n t plus sin omega n t. There was no exponentially decaying term. That means if damping is not present there, we have already discussed, the amplitude of motion will not get reduced. It will vibrate on the same amplitude over the period of time, right? So this is the general solution for the viscously damped fluid case and for the displacement case. Now, if you differentiate it with respect to T1, you will get the velocity response. If you differentiate it with respect to T twice, you will get the acceleration response of this system. Now, second case. So, here we have seen for the under damped case, the vibration will occur, right? The vibration will occur. Now, we will see for the critically damped and over damped system, these systems will be, aperiodic. Any kind of oscillation will not occur. So now the critically damped system. Critically damped. Already we have seen that the critically damping is the damping required to completely diminishes the vibration energy from the system. So critically damped system, zeta is equals to 1. That means C is equals to CCR. Now, for this case, if we simplify the root, so this is the general solution. I have written it here. General solution xt is equals to e to the power xi omega nt d1. I have considered the constant as g1 dash, given the different notation. You can give it a, b, c, d, e, f, or any kind of notations, and d2 dash. Now, look at here. Cos under root of 1 minus xi square omega n. So, zeta is equals to 1. That means this part will be equals to 1. And this part, look here, omega n 1 minus zeta square. So instead of this, we can write it down omega d. Already you have seen the concept of the damped natural frequency. The damped natural frequency is nothing but the natural frequency multiplied by under root of 1 minus damping ratio square. Now, put this in this solution and simplify it. We will have xt is equals to e to the power minus omega nt d1 dash plus d2 dash omega dt. So again, if we simplify it, x of t will nothing but e to the power minus omega nt d1 dash plus d2 dash t, where d2 is nothing but d1 dash omega d. Now d1 and d2 we can easily calculate from the initial conditions. Say initial conditions at t equals to 0, the initial displacement is x naught. At t equals to 0, the initial velocity is x dot naught. That means we are providing x dot and x dot naught, initial displacement and initial velocity. Now, we can easily simplify. At t equals to 0, put all these things in the equation, you will get x naught is equals to d1 dash, or d1 dash is equals to nothing but x naught. And again, differentiate it with respect to t1s, because we have the velocity initial conditions also, so we need to differentiate the displacement response equation. Then we will get the we can impose the initial conditions. Okay, so after simplifying, if we impose the initial conditions, we will find out d2 as x naught dot plus x dot x naught omega n. So we have d1 and d2. We have the general solution like this here. Now we can easily put all these values in these equations and we can find out the solution for the critically damped case. So this is the general solution for the critically damped case. Xt is nothing but e to the power minus omega nt x naught plus x naught is nothing but the d1 term or d1 dash term plus x naught dot plus x naught omega n, like this. So that was my equation. Xt was e to the power minus omega nt d1 dash plus d2t. Just put the value of d1 and d2, you will get the solution like this. So look here, it's the equation, it's a aperiodic equation, so that means no oscillations will occur, and as t gets to infinity, this term will tends to 0 and x of t will also tends to 0. That means So for example, here for a system, we are providing initial displacement, we are providing initial velocity, and the system is critically damped. So what will happen? It will be, at the equilibrium position quickly. So there is no oscillation will occur for this case. That means as soon as we provide the initial conditions, it will, go to the equilibrium position, and even it reaches the equilibrium position faster than the overdamped system, because the critically damped system, the main, uh, you know main logic behind it is to, diminish all the vibration energy from the systems. So critically damped system, it's aperiodic, no oscillation will occur, it's not harmonic. So if we provide some initial conditions and initial velocity and initial displacement, what will occur? At time increases, it will reach up to the static equilibrium positions. Okay, great. So example of the critically damped system: shock absorber of a car, of a bike. As soon as that system undergoes some initial velocity and displacement, its motto will be to, you know revert back the system to the equilibrium position, so that the comfort of the rider, or comfort of the passengers will not hampered, right? Or if we provide some initial displacement only, so the car will look like this. So if we provide some initial displacement, say x naught, it will look like this, it will come to zero position, it will not oscillate or vibrate. So critically damped system is not harmonic, it's aperiodic type of system. And the motto of this kind of system is very simple. As soon as possible, the vibration energy, or the energy of the vibration system, should be diminishes. Now we have another conditions, the overdamped case 3. So in overdamped system, the zeta value is greater than 1. That means in that system, the damping present in that system is greater than the critical damping. That means already there are surplus damping present on the system. So for this type of system, zeta greater than 1, that means we will have two real roots. So just put this in the general solution, d1 e to the power s1t, d2 e to the power s2t, and you will get the equation like this. Now d1 and d2, like previous one, we can easily solve for d1 and d2, and we can solve for d1 and d2 using the initial conditions. Obviously, using the initial conditions, we need to use the initial conditions. Using the initial conditions, we can find out the value of d1 and d2, and finally lead to the general equation of motion. And it's also not harmonic. Okay, so oscillation will not occur. So response or motion will not occur for this system also. But some phenomena, like for the overdamped system, say if we have two systems, critically damped systems and overdamped system, which will reach to the equilibrium fast. Obviously, critically damped system will reach to the equilibrium faster. So this is the critically damped system. And if we plot the overdamped system will, the curve will look like this. It will also be in the equilibrium positions, but little slower. Like we have the automatic door closer. We open up the door and leave it. It will slowly go to its equilibrium positions. But if we, design that door with a critically damped system, what will happen? As long as we just leave the door shut, it will close the door, right? So now for this system, we will use the overdamped case. So here, for the damped free vibration case, we have seen there may be three cases depending on the damping ratio. First case, where the damping ratio is less than 1. That means the damping present on the system C is less than the critical damping, where we have seen the final equation of motion, or the final solution for the equation of motion look like xt is equals to e to the power xi omega nt, 1 exponentially decaying curve, a cos omega dt plus b sin omega dt. Also we have solved for a and b, and this is the final equation for the displacement of the damped free vibration and for the underdamped cases where the oscillation will occur, system will vibrate and the amplitude will get diminishes as per the quantity of damping. Then we have seen for the critically damped system, for the critically damped case, it's an aperiodic time of system or the motion. The motion will not cross the zero, or it will not vibrate. And for the overdamped system also, we have seen that it's also an aperiodic system. The vibration, that motion will harmonic will not occur. But for the overdamped system, take more time to be in the equilibrium position than your underdamped system. Example of underdamped system, any kind of engineering applications, your buildings, bridges, all these things, underdamped system goes under the system. Critically damped system, the shock absorber of a shock absorber of a bike or car. And underdamped system, the automatic door closer system. You know that damper thing was there in the top of the door, that actually designed at overdamped system. Great. Now we have a concept of logarithmic decrement. So for the for the damped free case, we have seen that the amplitude of the motion will get diminishes over the period of time because damping is present there. And if we see the solution for the equation, e to the power zeta omega nt is also there. E to the power minus, this is the actually decaying envelope. E to the power zeta omega nt, what was the equation? A cos omega dt plus b sin omega dt. Right? Now, first let's understand the definition of the logarithmic decrement. Then we will understand from the logarithmic decrement how we can find out the value of xi, that means damping, from the free vibration response case. Okay, it's a very important phenomena. From where? From the number of cycles and from the free vibration response, either it can be displacement response, it can be acceleration response, we can directly calculate the value of the xi. So what we call the logarithmic decrement, the definition of the logarithmic decrement, it's like says like that: logarithmic decrement is defined as the natural logarithm of the ratios of the two successive peak amplitude, because the amplitude is reducing. So two successive peak amplitude, if we can find out, if we take the ratio and take the natural log, we'll find out the logarithmic decrement. Say for example, here we have a system, and the first peak amplitude we are taking here, and second peak amplitude we are taking here, peak amplitudes. So for example, x t1, at t1 time instant I am taking, and also I am taking the peak amplitude u2 is nothing but the peak amplitude at x t1 plus, say we are taking at time period td, damped time period. Great. So for T1, what will be the response? It's nothing but e to the power xi omega n T1 x naught cos omega d T1 x naught dot naught xi omega n x naught sin omega d T1 divided by omega d. Now at T1 plus d, that means after one cycle, that means two peak successive amplitude. After one cycle, we will have, instead of T1, you need to write it T1 plus TD. So first I'm taking the peak amplitude at T1, second T1 plus TD. So where I have two successive peak amplitude. So what will be the ratio? So obviously this is the harmonic function cos and sine. It will repeat itself after its time period. So this term will get cancelled out and we will left out with this part. So what is the ratio of the two successive amplitude? X of T1 divided by X T1 plus TD will be nothing but e to the power zeta omega n T1 divided by e to the power zeta omega n T1 plus TD. Now if I simplify it little bit, so what I get? E to the power minus zeta omega n T1 multiplied by e to the power zeta omega n TD. So this term and this term get cancelled out. What I left with, the ratio of the two successive peak amplitude u1 by u2 is nothing but x of t1 divided by x of t1 plus td is nothing but e to the power xi omega n td. Till now, we have not taken the natural logarithm. But the definition says the logarithmic decrement is the uh, natural logarithm of the ratio of the two peak successive or two successive peak amplitude. So we have calculated the ratios of the two successive peak amplitude of a damped free vibration case. Now take the natural logarithm. What will happen? So del is nothing but the logarithmic decrement is nothing but ln of u1 by u2. That means ln of e to the power xi omega n td. So del equals to nothing but xi omega n and td. Now simplify it little bit. What we will get? We know omega d is nothing but omega n under root of 1 minus xi square. So what will happen? Zeta multiplied by, instead of omega d, I am writing it in terms of omega n, I am writing it in terms of omega d, damping, because damping is present here, so it's more convenient to write it xi square into, what do you mean by say td? Td is nothing but twice pi by omega d. So omega d cancel out, we left out with del is equals to nothing but twice pi xi by under root of 1 minus zeta square. So this is the expression for the logarithmic decrement. So what the definition says, it's nothing but the natural logarithm of the ratios of the two peak successive amplitude of a underdamped free vibration case. Now if the xi value is very small, xi is very small, so we can neglect this part. So we left with del logarithmic decrement is nothing but twice pi xi. Now if we plot this del versus zeta, actually logarithmic decrement is this. If we, for the small value of xi, if we neglect that denominator part, so it will look like, the plot will look like this. Up to higher values of xi, will get linear, and if we consider this term for the higher values of xi, so it will get linear. So for the smaller values, we can see there is no difference between that denominator part I am taking or not. So for the small values of zeta, we can directly say, okay, my logarithmic decrement del is nothing but twice pi xi. Right? Now, what I already said, that from the logarithmic decrement, we can also calculate the damping. So it's a measure of damping. So if we have, say for example, we have done some free vibration test, and we have the displacement response and acceleration response. Say we have x of t. We have done some free vibration case on a structure, and we have some displacement response over time, or we have acceleration response over time. So from the displacement or acceleration response, how we can find out the damping ratio, we can just go through it. We will just go through it. So from the logarithmic decrement, from the concept of the logarithmic decrement, we can easily find it out. So for the just recall the definition of the logarithmic decrement. It says it's nothing but the ratios or the natural logarithm of the ratios of the two successive peaks. So if I have j number of cycles in this time series, if there are j number of cycles, so ui and ui plus 1, that means two successive peak amplitude, we have e to the power delta, right? Because we have just solved it. For the two peak successive amplitude, u1 and u2 is nothing but e to the power xi omega n t. And just I have written it down like this. Um, e to the power delta. Delta is nothing but your twice pi xi, or you can write it down in another way, in a simplified way also. So for this is for one cycle. Now if we have j number of cycle, so I and u I plus j will be nothing but your j delta, right? Now take the log both side. So what will happen if we take the log both side? J delta will be equals to natural logarithm of my first peak amplitude and the peak amplitude after jth cycle, right? Now delta is equals to what I can write? Delta is equals to 1 by j ln ui plus j. Amplitude plus I plus j amplitude. Now is equals to, we can write del is equals to twice pi xi. So now simplify this equation. From this equation, what we will get? Xi is equals to nothing but 1 by twice pi j. So we have twice pi xi is equals to 1 by j ln ui by ui plus j. So simplify it, you will find out the value of zeta. So zeta is equals to nothing but 1 by twice pi j. J is the number of cycles. Oh, we will solve few problems so that things will get clear, more clear. So ln ui divided by ui plus j. So if we have the displacement response, so this is the displacement response of a free vibration case. So we can calculate the zeta. If we have the acceleration response, similarly, the zeta can be calculated as 1 by twice pi j, the number of cycles, multiplied by ln ui double dot plus ui double dot I plus j. So by this way, from the concept of logarithmic decrement and from the free vibration test, we can find out the damping of a system. So we will see few examples so that things will get more clear. So till now, what we have uh, discussed, we have derived the equation of motion for undamped free vibration case where damping is not present. So the equation of motion was m x double dot t plus kxt equals to 0, and we solve the equation and we find out the solution for the displacement. So this is the displacement response of undamped free vibration case. Now we have already also defined for the damped free vibration case, and for the damped free vibration case, more precisely for the underdamped system, we get the uh, oscillations and harmonics will occur, and this we derive it as a form of xt is equals to the exponentially decaying term e to the power zeta omega nt under bracket a cos omega dt plus b sin omega dt. A and b we can find out from the initial conditions. A is nothing but x naught and b is x dot naught plus zeta omega n x naught by omega d. And omega d we have seen, because damping is not present here for this system, omega n natural frequency, this is damped natural frequency, and damped natural frequency and frequency, the relation is nothing but omega d is equals to omega n under root of 1 minus s square. So for free vibration case, we can get the displacement response at any point using this equation, and if we differentiate it with respect to t1, we get the velocity response at any point, and if we differentiate with respect to twice, we will get the acceleration response twice. So previously we already have defined it. And for the damped free vibration case and precisely under damped system, we will get the displacement response using this equation, x of t is equals to, so the responses look like if we provide some initial displacement and leave it to vibrate. So for example, we provide some initial displacement for the underdamped system and leave it vibrate, it will vibrate like this. The amplitude will not get diminishes. For the dam case or the underdamped cases, if we provide some initial displacement and leave it to vibrate, what will happen? Depending on the damping ratio, the amplitude will get diminishes over time. T versus x of t. T. And this e to the power xi omega at nt will be the envelope of this decay, and from this envelope of the decay, using the concept of logarithmic decrement, we can also find out the value of zeta from the free vibration test. Okay, so now we will solve some problems one by one. Great. So first read out that first problem. So the first problem says the calculate the displacement at t equals to 1 second of a damped SDOF system where the damping ratio, the zeta value here, eta is denoted. Okay, eta and zeta both represents the damping. So here zeta is 10%. The initial conditions are given. The initial displacement is 1.25 centimeter. Initial velocity is given 25 centimeter per second, and the cyclic natural frequency is also given. Okay, what do we need to find out? We need to find out the displacement at t equals to 1 second. So how we can find out? It's a damped free vibration. So what was the general equation for the displacement case? Just recall, x of t is nothing but e to the power minus zeta omega n t x dot cos omega dt plus x naught dot, that means the initial velocity, plus x naught zeta omega n divided by omega d sine omega d, right? You have x naught value, you have x dot naught value, you have the frequency, but in the term of cyclic frequency, not the circular frequency, because omega d is the damped circular frequency. So we have already covered the concept of circular and cyclic frequency. Just go back and see the previous slide, you will get it. So the damping ratio 10%, that means 0.1. Initial condition x naught 1.25 centimeter, the initial velocity 25 centimeter per second. We have the frequency, circular frequency, so we need to convert it into a cyclic frequency. We have to convert it into circular frequency. So omega n is nothing but twice pi f. So we have 31.416 rad per second. Now here look, we need the natural frequency, we have the damped natural frequency. So what will be the value of damped natural frequency? Omega d will be nothing but omega n under root of 1 minus zeta square. So the value comes as this. Now we have the equation for displacement at any time instant. Put all these values in these equations at t equals to 1. So t equals to 1, zeta value is nothing but 0.1, omega n 31.416, t 1, then initial displacement 1.25 cos omega t, t is equals to 1, plus initial velocity plus initial displacement into 0.1, that means xi, this part xi omega n divided by omega d sine omega dt. Now if you solve it, you will get that the displacement of this system will be equals to 0.471 mm at t equals to 1 second. Just go through the problem once again. It's very simple. Great. Now, in this question, if asked what will be the velocity at t equals to 2 seconds. So here we have calculated the displacement. If you need to calculate the velocity, what will you need to do? You need to differentiate this equation first with respect to t, and then put all these values on this x dot t equation. Great. Right. Now let's solve another problem. So in a damped SDF system, the mass, stiffness, and damping properties are provided. Mass is 100 kg. Stiffness is 45500 Newton per meter. Damping is 15%. Damping ratio is 15%. That means 0.15. Now find out the damped frequency of the free vibration and critical damping of the system. Damped frequency, that means we need to find out omega d, and critical damping also. That means we need to find out the CCR. Critical damping, what I said, what is the definition for the critical damping? Is nothing but the damping required to completely diminishes the vibration energy of the system, right? So how we can solve? First, what we need to calculate? We need to calculate the natural frequency omega n. Omega n is nothing but under root of k by m. You have the value of k, you have the value of m, put all these things and please check the calculation once again. So 21.331 rad per second. Great. Now we need to find out the omega d, damping, damped natural frequency. What will be it? Omega n under root of 1 minus zeta square. Here put all these values, you will get 21.09 rad per second. Now what will be the critical damping? CCR, already we have defined the formula for CCR. It's a function of mass and stiffness twice pi omega n. Omega n already we have calculated and this comes as this. Great. Now in this question, what it asks, find out the ratio of two successive peak amplitude of free vibration of a damped SDF system if viscous damping ratio is 0.0. That means 2% damping is present on the system. So how we can calculate it? So zeta or eta is provided 0.02. We know del is nothing but ln of two peak successive amplitude x2, right? So again we know the del is equals to nothing but twice pi zeta is equals to ln of x1 by x2. Now we have twice pi, we have the zeta value 0.02 is equals to ln x1 by x2. So you need to find out the ratios x1 by x2. So just calculate x1 by x2 is equals to nothing but e to the power this. So that comes as 1.134. Right? Understood? Now next question. So for a viscous damped SDF system, it is observed that the amplitude of the free vibration decreases from 1 to 0.5 in 3 seconds. So first amplitude, say xi was or x1 was 1, and after 3 cycle I plus 3 it got reduced to 0.5. Now calculate the logarithmic decrement and damping ratio of the system. Now damping ratio, what I just discussed, like we can calculate the damping ratio from the displacement response also if the number of cycles and the peak amplitude are known. So x1 is nothing but the first peak amplitude is 1. X3 after 3 cycle is nothing but 0.5. So we know from the logarithmic decrement thing, ln x1 by x3 is nothing but j of delta. J is the number of cycles, right? So here we have 3 cycles. So ln x1 by x3 is equals to 3 delta, right? Now delta, you can find out delta. That means logarithmic decrement. Delta is nothing but 1 by 3 ln 1 by 0.5. And that comes as 0.231. Okay. Now we know that delta is equals to nothing but twice pi zeta or eta. Now equate it, twice pi zeta. So zeta is equals to nothing but del by twice pi. So zeta will become as 0.0368. That means 3.68% damping is present there, right? So we have calculated the logarithmic decrement. Logarithmic decrement first comes as this, and the damping ratio comes as this, right? So now let's quickly solve few more examples and we will close this. So for the damping purpose, we have few, yeah, here we have few more example, like the stiffness and damping properties. The stiffness and damping properties of a mass spring damper system are to be determined, right, by a free vibration test. The mass is given as m is equals to 0.1 lb per second square per inch. In now these are in APS unit. In this test, mass is displaced 1 inch by the hydraulic jack. That means the initial displacement is provided 1 inch by the jack and then suddenly release. Okay, so initial displacement, that means the first peak amplitude was 1 inch. Now after 20 complete cycles, that means j is equals to 20. So after 20 complete cycle, my peak amplitude becomes 0.2. So first peak amplitude x1 was 1 inch, and after 20 cycles the amplitude becomes 0.2. Determine the stiffness, damping coefficient. Stiffness and damping coefficients. Okay. So let's see how we can find it out. So we know from the logarithmic decrement that logarithmic decrement ln u1 and 1 plus j, that means the first amplitude and j the amplitude, we have j into delta. That means this part is delta twice pi xi into del. So xi will be equals to nothing but 1 by twice pi j ln u1 by u1 plus j. Already we have derived this formula here from the displacement response curve, how we can find out the damping ratios here, this formula. Now put all these values in this formula and try to solve it. Yeah. So zeta comes as 1.28%. 1.28% zeta means it's very small, right? Great. So if zeta is very small, we can consider that TD, damping frequency, is equals to Tn, natural frequency. Because look, if we write down the omega d is equals to omega n under root of 1 minus zeta square. Now zeta is very small, that means we can neglect this part. That means omega d becomes omega n. So what will be the damped time period? It's nothing but this, and subsequently the natural frequency omega n is equals to twice pi by Tn. Or we can directly write like omega d is equals to omega n, and omega d already find it out. So that comes as omega n comes as 41.89 rad per second. Now how we can find out the stiffness and also damping coefficient C? Not they have not asked for the xi, they have asked for the C. So how we can calculate it? We have the omega n we have the omega n value, right? We have mm, the cycles, 20 cycles here. Okay, we can easily calculate it like this from the natural frequency thing. So k is nothing but m omega n square, because omega n we know is nothing but under root of k by m. So k will become per inch. Now I can find out the c value. So we know c by c cr is zeta. That means is the ratio of the damping present in the system divided by critical damping is xi. So again we know that CCR we can write twice m omega n is equals to zeta. So C we can write it down. C is nothing but twice m omega n zeta. Now put all these things, you will find out the value as this. Clear? Okay. We will solve another example, one example, then we will close it. Like here, see the example. So the weight of a wooden block, the weight of the wooden block shown in the figure is 10 lb and the spring stiffness is 100 lb per inch. A bullet weight of 5 lb, that means a bullet of that weight hit this mass at a speed of 60 feet per second and embedded into the system. Okay, that means the bullet actually providing the initial, conditions or initial velocity to the system. That means it's a free vibration case where we need to find out the resulting motion of the system. Damping are also not present in there. So from where, how can we calculate it? So from the conservation of motion, we know that m naught v naught, m naught is the mass of the bullet and v naught is the velocity of the bullet, is nothing but m mass of the system plus m naught total mass into total motion of the system, because the bullet itself is providing the initial conditions, right? So the motion also will be associated with the total mass of the bullet plus mass of the system. So here if we simplify the equation, u dot naught is equals to, we get this 34.41 inch per second, right? That means that initial velocity the bullet inserted to this or generated or initiated in the system. Now, after the impact, mass will be total mass, stiffness will be this, natural frequency will be nothing but under root of k by m plus m naught, right? And that comes as 60.63 rad per second, right? Now, initial conditions we find out, like u0 is equals to 0, u naught 0 is equals to this. Now we have the equation of motion for the undamped free vibration, underdamped, sorry, undamped free vibration case, because damping was not present there. So x of t or u of t, you can write it down, x naught cos omega n t plus x dot naught by omega n sine omega n t. Now put all these values. X dot is 0 and x naught dot actually you have calculated as u dot naught. Now put these values here. U dot naught is 34.41. Omega n we have calculated 60.63. Sine 60.63 t. So this will be the equation for the displacement of the system. Now here look, t is sitting over here. Now you can calculate t is equals to 1, t is equals to 2, t is equals to 3, and so on and so on. So if you have the equation for the displacement, you can solve it for different times. So here this problem is also the undamped free vibration case problem, where the initial velocity of the system is initiated using a bullet, right? Now similar kind of example here, you just solve it. Similar kind of thing I have written it down, step by step, so you can easily correlate and calculate it. Please go through it and try to solve it. Okay, so today what we covered, just quickly go through it and we will sum up. So today what happened, I need to you know mm, take it twice. One, when you were online, and again because that video was not recorded properly, so I need to record it again. It's like double work for me. It's okay, no problem. I promise that I will give that video lecture to you. That's why. So we have solved here three things. First, we understood what we call the free vibration. Then we solved the equation of motion for the undamped free vibration case. Then we seen how to calculate the displacement, velocity, even phase at any time. Then we we solve different kind of problems here. Then we move to damped free vibration, where we have seen a damping is present and only for the underdamped system or underdamped cases. Here, for the underdamped cases, only the harmonic or acceleration will occur, and we will have this response decay curve. And for the two cases, for the critically damped system and for the overdamped system, there will be aperiodic things. And we covered the concept of logarithmic decrement. It's nothing but the natural logarithm of the ratio of the two successive peak amplitude. And from this, it's a very important phenomena. We have seen that if we have the displacement or acceleration response of free vibration, we can easily calculate the damping ratio from the logarithmic decrement thing. And then we solve different kind of problems related to the logarithmic decrement, related to the damped natural frequency, damped natural time period, and all these things. Okay, then I hope that if you go through this video and this note carefully, you can able to solve all kind of problems. If you face any kind of difficulties or any doubt, please mail me to this mail ID. So yeah, my mail ID is written over here. So you can mail it there. I am very much actually active on that there. So you just mail me if you find any kind of difficulty during this lecture. I will try to solve this as soon as possible. Okay, then for today, I am closing it now, and we will meet on the next session. And from the next session, I will make sure and that recording is on and recording is working properly. Okay, then thank you.